I'm Matt, and this is Marty, and we're going to show you how to convert any data into music using Python. As an example, I'll show you how I converted data of lunar impact craters into music with my project System Sounds. It's a simple example of a musical sonification, and I'll break down the code into many small steps so it's accessible to beginners. Before you start, you're going to need to have Python installed on your computer, and I'll be using a program called jupyter to write and run the Python script. I'm also going to use a few Python libraries, but you can install those along the way. All right, so here's how it's going to work. We're going to start with our data as a CSV file. So you can use any data you like as long as it's in a CSV file. And our first job is to convert or map that data into musical notes. We're going to save those musical notes as MIDI events in what's called a MIDI file. To do that, we're going to use Python. So the Python script is where you're going to do your sonification design and also where you're going to implement that design, kind of in parallel. One of the first questions you should probably answer is, what is the sonification mapping? So which elements of the data, which columns of the data get mapped to which musical parameters? What about the data controls what about the sound? That's the mapping. And once you've made that choice, there's still a whole set of other choices to be made. So for each mapping, you're going to have to decide the polarity of the mapping. So that means, for example, do you want higher numbers in your data to correspond to higher musical pitches or lower musical pitches, or higher volumes or lower volumes? That's a choice you have to make, and it can have a really big effect on how people experience and understand your sonification. You'll also have to decide on the range of your mapping. So maybe, for example, what is the range of notes you're going to map the data to, or the range of volumes? And you also have to decide the scaling of the mapping. And by that, I mean, what's the exact mathematical form of the mapping? How does the data get transformed into other parameters? So is it a linear mapping or a nonlinear mapping? I'm going to call that the scaling. So once you've got your musical notes encoded in this MIDI file, what we want to do eventually with that is hear it. We want to turn it into audio. So that could be as a WAV file or as an MP3 file at the end of the chain. And to do that, all you have to do is load the MIDI file in a digital audio workstation, or a DAW. I'm going to use Logic Pro X, but there's several other options. Ableton and GarageBand are popular, and there's also options that are available for free online. And so this is where you basically do your music production stage. You get to bring the data to life by giving it whatever sounds or instruments you like. You get to add effects and layers, and you can really go nuts and make it into something more musical if that's what you're after. So I've got the folder here, which has the Jupyter notebook we're going to be working out of and the data itself. And so I want to launch Jupyter Lab from within that folder. So I've got a terminal here, change directory into that folder, and then type Jupyter Lab and return. And that opens up your Jupyter Lab session, which is over here. Okay, so we're going to start by just looking at the data we have to work with. This is a list of 111 craters on the moon. These are all of the ones that are bigger than 10 kilometers across and that have accurate age estimates. So you can see some of them have official names. They've all got a longitude and latitude, which we're not going to use here, but you can use that for your own sonifications. And then they have a diameter measured in kilometers and an age measured in millions of years. So we're going to use the diameter and the age. Let's open up the Jupyter notebook. Okay, so this notebook is going to convert that data into a MIDI file. And here is the sonification mapping. We're going to start with the age column and map that to time in the obvious way. Right? We want them to unfold in time just faster than they actually did, so we don't have to wait around for a billion years. So that one's kind of obvious. And then we're going to use the diameters to control the pitch of the note you hear. And we're also going to use the diameters to control the velocity of the note you hear. So in MIDI, velocity is like a combination of volume and intensity. And then on the right, we have the polarity of each of these mappings. So for pitch, this may sound backwards, but I think it makes more intuitive sense to have the larger craters produce the lower pitched sounds. And that's because bigger objects can produce lower pitch sounds. So I think that matches more in my head, at least. And for velocity, I think it makes even more intuitive sense to have the larger craters be the louder and more intense sounds, because they were created with more intense asteroid impacts. Okay, and that's kind of what we're doing here. We're kind of trying to listen to the record of the asteroid impacts that caused these craters. All right, so first step is to just load that data into the session. And for that, I'd like to use the pandas library. It's a really good library for working with databases. And so we're going to tell it to read that CSV. And it's going to return something called a data frame, or DF. And so that's storing all of the data in that CSV file, but now it's in a form we can work with. So this will load the data frame. If you actually want to just see the first 5 lines of that data frame to make sure everything worked, you can run df.head. So to run a cell in Jupyter, you can press shift then return, or just use the plus sign up here, or the play sign, which means run here. Okay, so running that gets the data and shows us our first 5 lines. So there they are. You can see they're not in any particular order. So if you wanted to, it's pretty easy to sort them. It's actually not going to matter for the way we do the sonification, but there is a sort values function, and we're going to tell it to sort by the column called age, and we want it to be ascending is false. We want it to be descending because we want the biggest age to be the first in the list, because that's the oldest crater. It happened first. Okay, so now if we run this cell, they're in order of when they actually occurred. So the first one was 1,324,000,000 years ago. Okay, and while we're here, I'm just going to make a little convenience variable to make it more obvious what's happening later. So I'm going to define n impacts, which is just the number of rows in that data frame. And printing that gives us 111, so we've got them all here. Okay, the next step, I like to just plot the data, just to look at the overall patterns and structure in the data, because that might inform your sonification choices. Probably should. So for plotting, I'm just going to use the standard matplotlib library. And the way you get the columns out of a data frame is just to reference those columns by their name. And then .values means give me all the values from in that column. So that'll give us our ages in what's called an array. And the same thing for diameters. And the fact that they're arrays and not lists means we can do mathematical operations on these objects, which will make things a little, which will be nice as we go. Okay, so we've got the ages and diameters. Let's just make a scatter plot of ages versus diameters, and we'll make the size of the dots be also controlled by the diameters, just so it's easier to see which ones are bigger craters. Okay, so that's what our data looks like. You can see it's automatically flipped the time axis, right? Because it's increasing it in age, which is actually going backwards in time. So that's fine, you can work with this, but we're going to flip that because we want to hear things happen in the order that they actually did happen in. So if you want to see what that looks like, you can just invert that axis essentially. So let's define times in millions of years by taking the oldest crater and then subtracting the value of the age of each other crater. Okay, that'll return their times relative to when the first impact in our data happened. So the time since impact 0 will be plotted now. So same graph, just the x-axis is inverted. And so now you can see kind of the way the music's going to unfold. You get a little better idea. Okay, you can see there's many, many smaller craters and very few large craters. Okay, and that's because the bigger asteroids are much more rare. And you can also see they kind of pick up the pace here over time. So that's good from a musical standpoint because it means things are going to develop and get a little more interesting, right? You want to look for shapes like that if your goal is to make something musical. But It's already there in the record. We don't have to do anything. Okay, so then next we're going to write a general mapping function. This is something you have to do all the time in sonification, because what you're doing is mapping values from one range to another range. So let's just write a simple function that'll do that, so we can use that function over and over again. So I've written a very simple function called mapValue. It takes an input value, which currently lies in the range min value to max value, and it maps that into a new range, min result, max result, and returns the result. Okay, so you don't have to worry about what's going on inside the function. It's not too complicated, but we just have to know how it works, what the result's going to be. Okay, so as an example, let's just say your value was 5, and it came from data that went from 1 to 10, so it's kind of in the middle, and you want to map that to a new range, which say goes from 100 to 200. Could be anything. Okay, so I'm expecting something near 150, but not quite, because 5 wasn't exactly in between 1 and 10. And so, okay, that worked. And you can test the endpoints. You know, if you put in 1, which is the lowest value in the range, you get back 100, that's right. 10 should give you back 200, that's right. Okay, and notice that I'm putting in integers, right? All these happen to be integers right now, but it's returning a float. There's a decimal there. Okay, that's going to be important later. Sometimes maybe we don't want a float, so we'll have to do something about it. Okay, so that's our mapping function. Let's tackle the actual mapping then. So let's start by compressing time. So we're kind of mapping the ages to time within a much more limited range. There's two kind of ways you can think about this. So what I'm calling option 1 is where you set a conversion factor to compress time. You're saying how much do you want to be compressed by in a particular way. So our data is already in millions of years. So one way is to say how many millions of years do you want to correspond to 1 beat. So I've chosen 25 here. And once you do that, you can just take all of the times in your times array and divide that by million years per beat. That'll just compress everything. So if you look at this, the array it returns, which I'm calling T data for time data, you've got an array of numbers and goes, in this case, from 0 to 52.8. Okay, so that would mean the beat of the last note is at 52.8. And you may be wondering why I'm not talking about seconds. And the way we're going to set it up, these will also correspond to seconds, but the way MIDI works is it expresses time in beats. So we have to think in beats when we're making the MIDI file. But we'll make a choice that will make 1 beat be 1 second. So it's not going to matter. But if you wanted to just print the duration in beats here, print that last number. So let's define duration in beats is the maximum time and 52.8 beats. Okay, so that's compressed time. The other way is to just set an overall duration you want and let it figure out the conversion factor. So for that, we can use our mapping function. So let's say you want the duration to be 52.8 beats. Okay, you can use your map value function and map the data, which is currently in millions of years, and it currently runs from 0 to the maximum value in that array. And you want to map all those numbers into a new range that goes from 0 to your duration in beats. Okay, and that'll return T data. Okay, and that worked. So notice that you can put a whole array inside this map value function and it'll return a whole array. You don't have to do it one number at a time. Okay, so let's say you did that and then you were just curious how many millions of years per beat did that correspond to. That would be the maximum time divided by the duration in beats. That'd be million years per beat. And it gives back 25, which is what we expect. And we can change this to any duration you want, depending on what you want the experience to be. Okay, so that's all time measured in beats. If you want to think in terms of seconds, you can set a tempo. So that's measured in beats per minute. So I'm going to define BPM is 60. And with that choice, 1 beat is 1 second. So we don't have to worry about the distinction. So you can calculate duration in seconds. it'll work out to exactly the same as what we had for beats. Okay, so this will print that, and then it'll make a scatter plot. Okay, 52.8 seconds. So in other cases, you may map your data into a quantized grid. So maybe you want like every 100 million years to be a beat, okay? But then you want to have control over how fast that actually happens, the tempo of your piece. Then you have freedom to control that by changing the BPM. Okay, in our case, it doesn't matter because we're not lining up any of the actual data points with the beats. It's not on a grid. Okay, so the next thing I like to do is to normalize and scale the data. So this is the y-axis data, the diameters. Normalize means map it so that it goes from 0 to 1. So we can use our map value function to do that. You put in the diameters, which currently go from their minimum value to their maximum value, and then you map that to a new range, which is from 0 to 1. Okay, and then if we plot that, so we're plotting what it returns, which is the y data versus time, and we set the size of the data points in the scatter plot to be controlled by the y data, which is measuring diameter, and we get that nice plot. Okay, so the same plot we saw originally, essentially, except now the y-axis goes from 0 to 1. So maybe you're wondering why I did this, why I'm breaking this up instead of just doing the final mapping, why normalize first. And that's because I want a little more control over the mapping, over the scaling of the mapping. So notice that, as we saw before, there's many, many small craters, and they're all kind of bunched at the bottom. So if we map these y values to musical pitches, most of those small craters are going to be mapped to the same note. And maybe you want that. Maybe you want to communicate that there's a lot of them that are very, very small. In my case, I just want to communicate that there are many different sizes. So I want to kind of be able to hear the difference in size, even if the difference in size is small. And so the way to do that is to use a different nonlinear scaling with diameter. So for instance, before we plot, we're going to define a scaling parameter, which is 0.5, and bring all of those data points to the power of 0.5. And watch what happens with the graph when I run this cell. Okay, so it kind of just spread things out, especially in the bottom half. And so now it'll be easier to tell the difference between the crater sizes with pitch because they'll get mapped to different pitches. So this is a musical sonification, and there's certain goals for it. So this is totally legal to do. It depends on your goals for the sonification. Okay, so we've got our normalized and scaled data. And now comes the more creative part. We get to choose the musical notes that we're going to map to. So the way MIDI understands musical notes is with MIDI note numbers. So there's one MIDI note number for every note on a keyboard. Okay, and so here's a little sample. So the note called C3 corresponds to MIDI note number 48, and so on. So if you're a musician, you probably want to think in terms of the note names first. That's one way to do it. And then you just have to convert into these MIDI note numbers because that's what MIDI understands. So to do that conversion, I like to use this function called string to MIDI, which is in the AudioLazy library. AudioLazy is a very powerful library. This is just one of their kind of convenience functions. It's got several more like this that are really great for converting between note names and MIDI note numbers, or between either of those and note frequencies. So if you run string to MIDI on A0, that's the lowest note on a piano, that gives back 21. So that's MIDI note number of A0. And if you put in C in the third octave, you should get back 48, and you do. Okay, and also notice that these MIDI note numbers are integers. Okay, that's going to be important in a minute. Okay, so then what you can do is choose a set of notes to map your data to. So I'll just write them out explicitly here so you can see what's going on. So these would be the note names in 4 octaves of the C major scale. And this is a really common thing to do in sonification, to map your data to a few octaves of a certain scale. It's got a certain regularity to it. So that'll work. You could do that. Let's go with that choice for the time being. And let's convert those into MIDI note numbers. So you can do that in one line here by saying for every note name in the note names list, run that function to find its corresponding MIDI note number and add it to the list that we're making here. So if we print note MIDIs after running this, we should get a new list of MIDI note numbers. So 36 is C2, 38 is D2, and so on. Okay, so that'll work, but you can choose any notes you want, right? And for one thing, the major scale is not always the best choice because it has these notes that are really close together. E and F are right beside each other on a piano, same with B and C. And so if you play those together, it's going to be a little dissonant. And sometimes that dissonance is great and it's exactly what you want. Other times you want something more more inoffensive, let's say, more constant overall. So another popular choice with some safer notes is to use the major pentatonic scale. So that's just the C major scale with like removing those potentially offensive notes, the F and the B. Okay, so that's a common choice. In our case, we're going to go a little further, be a little less regular. And we're not even going to choose a regular scale. We're going to map the data to a certain chord, a certain voicing of a certain chord. So this happens to be a C major 13 sharp 11 chord, or you can think of it as notes from the C Lydian scale. And it's got a certain voicing, like a certain arrangement of notes to make up that chord. So you can see the note names in each octave are different. Okay, and I just wanted a Lydian scale because I wanted that kind of positive sound, but with a bit of an air of mystery for this. Okay, but you know, possibilities are endless here. Okay, so I'll go with that one. It'll override the previous ones, but let's just comment those out. And while we're here, let's just define another convenience variable to make things a little easier to follow later. Let's just save the number of notes in our list of note MIDIs, which is the same as note names. Okay, that's 23. So that's like the overall resolution of your mapping. If you wanted a higher resolution, you can just use more notes. Okay, so we've got our note MIDIs list ready to go. The next thing to do is to actually map the data into the corresponding MIDI note numbers. And as I said before, we're going to have the larger craters mapped to the lower notes. Okay, so here's a loop that'll do that. So this is we're defining a MIDI data empty list, and then we're going to use a for loop. So for every one of those impacts, we're going to run our map value function. It's going to take its current normalized Y data value, which currently goes from 0 to 1, and map that to a new range, n notes minus 1 to 0. Okay, so that may seem odd, but let's go back and see why that works. Okay, so let's say your Y data was 0. Okay, that's the smallest crater. This map value function is saying it's going to map the smallest crater into n notes minus 1. Okay, the reason we're doing that is because we're going to use that as a index to find the right element in that array, in that list of note MIDIs. So n notes minus 1 would be 22. So if I run note MIDIs 22, that's MIDI note number 93, which corresponds to A6. Okay, the smallest crater got mapped to the highest pitch note. And I control that polarity by the order of these two parameters, n notes minus 1 and 0. Okay, and on the other end, if your Y data value is 1, that's the biggest crater, that'll get mapped to 0. And the 0th element in the array, in the list, sorry, is the first element, which will be C1. Okay, so this minus 1 is because it's 0-based counting. Right? The first element is 0. The last element in the list is n notes minus 1, which is 22. Okay, so then we're using that index right here to find the corresponding note MIDI number, and adding that, appending it to our list. And notice I've got this round function here, right? That's because these note MIDIs have to be integers, but map value returns a float with a decimal. So this is going to round that so that they're all integers so that this step will work. Okay, and let's plot our MIDI data versus our time data, T data. Okay, and so now it's similar to the previous plots, except it's kind of flipped. Okay, this is showing you that the first thing you should hear is a kind of high note. There's going to be a big gap. You'll hear that note again, and then a few other notes, and then it should really pick up. Okay, so that's what how our music's going to evolve. So we've chosen our MIDI note numbers, or our musical pitches. Next, let's map the data to the note velocities. So here, our larger craters are going to have greater velocities. So that's a similar process, except velocity in MIDI can go from 0 to 127, which is also the same for the MIDI note numbers. But we don't want to use the full range because the velocity of 0 is going to be really, really faint. It's probably going to be hard to hear in our sonification. So we're going to set a minimum value for velocity of 35 and keep the maximum, its actual maximum, which is 127. And then for every one of those impacts, we're going to use our map value function again and map its current Y data value, which currently goes from 0 to 1, into our new range, which is our minimum velocity to our maximum velocity. And once again, we're going to have to round what it returns because note velocity also has to be an integer. You'll get an error later on if you don't do this step. Okay, so we'll do the same plot now, except we're going to control the size of the dots with the velocity to make sure everything's working. Okay, so that's how our music's going to unfold. You can see the biggest crater is going to be the lowest note at the bottom. It should happen just after 20 seconds or 20 beats, which will also be 20 seconds. And yeah, pretty much ready to go. Now we just have to save that data as a MIDI file. To do this, I like to use the MIDI util library. It has a class called MIDI file. So you make an instance of that class, make a MIDI file object with one track, because that's all we need. And then you add a tempo to that MIDI file. There's only one track, so that's on track 0. And we'll do this at the beginning of the piece, which is time 0. We set the tempo to the BPM we had already chosen, which was 60. And then for every one of the impacts, you're going to just add notes to that MIDI file. And the MIDI util library takes care of a bunch of things behind the scene. But when you add a note, these are the choices you've got. So you can put it on track 0. You have to, because it's a one-track file right now. On channel 0, because we only need one channel. And then the pitch is actually asking you for the MIDI note number, which is in our MIDI data list. The time is asking for the time data measured in beats. You can set a duration if you want for each note. I've set them all to 2 beats or seconds. You can use data to control that too if you want. Didn't really matter here. And then the volume is actually asking for the velocity, which we have in our velocity data list. Okay, and then once you've added all those notes to the MIDI file, these few lines will just create a new MIDI file and write that data to it. So if I run this cell, a new MIDI file should pop up. It didn't. Oh, there it is. Okay, so now I've got the MIDI file, and the next step is to open that in a digital audio workstation. So I've opened up a session in Logic Pro, and then I'm just going to drag that MIDI file we created into the session. And it's asking if I want to import tempo information, and yes, because we set it to 60. Okay, and so we can have a look at it here. You can see the MIDI notes. Okay, you can see that that low note near the bottom is red. That means high velocity. High notes at the top there are lower velocity, so it all looks pretty good. Right now it's on a default electric piano sound. Okay. Which I don't mind, but in the original version of this, we used a vibraphone. Okay, so let's see what that sounds like. Okay, and so we wanted something with a pretty strong attack, right? Because they're signifying asteroids hitting the moon. So we need something that has like a punch to it. We thought that fit pretty well. So it's pretty bare right now, right? Let's make this a little more palatable. So one thing you can do is just duplicate that same data on another track, on another instrument. So as a supporting instrument, let's use some violins. It's not the best violin sounds, but we'll go with it. So the reason I want to do this is that there's like huge gaps in the data, especially that big one. And I want something supporting that kind of sticks around a little longer. So violins can sustain, they won't have that sharp attack and decay. And then maybe I'll just make all of these violin notes a little longer. Okay. And maybe just to smooth it out a little more, I'll add some reverb. So I always like to use this Valhalla vintage verb. Let's use like a ridiculous amount of verb, 80%, a couple of seconds. Okay, it's just a supporting part, so it's okay if it's muddy. That's kind of the idea. Where are we at now? Okay, pretty good. That low note sounds a little weird, right? That's because it's like out of the range on a vibraphone, right? And the violin too. And so the really low notes on a vibraphone, you're kind of only hearing certain harmonics and not really the root. So if you're serious about this and you want notes that low, you should probably add in maybe like a synth bass or something, like a pure sine wave that can support that low root. Okay, so be aware of the natural range of your instrument. Here I'm just ignoring it, but we could fix it later if we wanted to. Okay, so next, it's still pretty bare and exposed, right? I need something to tie it together and to kind of ground the whole thing. So we're going to add a drone. And in the original version, we created a drone by converting the moon's topography into a sound wave. So we imagine kind of like playing the moon's surface with a giant record needle and spinning the moon. That would generate a sound wave because the two sides of the moon, the one that faces us and the one that doesn't, have different heights. So you get something like a regular sine wave with interesting information. So here's what that gives back. Okay, so really way too aggressive for what we're doing. We'll fix that in a second. It's kind of cool though, just like a slowly evolving drone that changes because different parts of the moon have different numbers of craters, different densities of craters. Okay, so for one thing, it's way too short. So in Logic, you can stretch things pretty easy. Let's stretch it a little more to a little longer than the MIDI data. And then let's shift the MIDI data over. So there's a bit of an intro. You can hear the drone and just kind of ease yourself into the piece. And then to make it a little less offensive, let's put a really big low pass on it. Okay, it's probably way too loud. And then just because I want to smooth it out more, back to my old favorite of extreme Valhalla vintage verb. Okay. That always makes the endings pretty nice too. It's just like really sweet, rich reverb at the very end. Pretty long gap here, but we tied this to visuals, so it didn't get too boring. All right, and so in just a few minutes, it's getting pretty close to the original that we posted. So have fun with it. Take your own data and make your own choices, and I'd love to hear what you come up with. Thanks for watching. Don't forget to like and subscribe, and check out part 2 of this series where I show you how to control almost any musical parameter with any data you choose. Also, let me know which video I should create next.